5 is dynamic forces. In topic 4, we did static forces. In static forces, we made use of Newton's first law of motion, equilibrium. And in that case, the sum of the forces equals 0. So we did lefts equal rights, and ups equal downs, and the ramps equal down the ramps. In topic 5, we're going to make use of Newton's second law. So with the dynamic part being that there's an acceleration and a net force. So the net force in this case is not 0, and the net force produces an acceleration. But there's a lot that we learned already from topic 4 that we'll use here, mainly free body diagrams and the forces that are involved with those. So the forces themselves don't change. 5.1, well, 5.1 is horizontal linear problems, where we'll apply the second law. And in that case, the first part we're going to do is doing work against friction. So when we do this, or problems with the second law, one force is typically larger, like a push force is larger than, say, a friction force. And we might still have Fg down and F perpendicular. And so in that case, not only is the sum of the forces mass times acceleration, but it's also the bigger force, or the winner, it wins out, minus the loser, or the smaller force, is also the sum of the forces. Putting these two together, we get the winner minus the loser equals mass times acceleration, or the bigger minus the smaller force in magnitude. So here's an example. A person pushes a 60 kilogram holiday gift with no friction. In this example, forward with a force of 300 newtons without friction. I said it. Sorry. What is the expected acceleration? So our FBD that we start with here has this push force, an upward F perpendicular and a downward Fg. And so in this case, the sum of the forces is mass times acceleration, but there's only one force in that x direction, so the loser is 0, and equals mass times acceleration. So the push force is 300 newtons. The mass is 60 kilograms. So we could see that A is 300 newtons over 60 kilograms. But since a newton is kilograms times meter per second, that's going to be 5 meters per second squared. I'm sorry, a newton is a kilogram times meters per second squared. Okay, the actual acceleration was only 2, let's say. So this is a continuation. Suppose the actual acceleration was only 2 meters. What is the mu between the holiday gift and the floor? Well, in that case, we're going to have our push force, but we also have on it some friction. But we have a positive acceleration, so we know the push force is winning out over the friction force. So the sum of the forces is mass times acceleration, but it's also that F push minus the friction. And we know what the push was from the previous problem of 300 newtons minus mu F perpendicular equals the mass of 60 kilograms, quite the holiday gift, times A, which is 2 meters per second squared. And in that case, we want to know what mu is. We can fill in what F perpendicular is too, because it's equal and opposite to Fg, so it will be 600 newtons. This would be 120 newtons over here. So if we subtract the 300 newtons over, we get minus mu times 600 newtons equals minus 180 newtons. So mu equals minus 180 divided by 600, or 0.3. Okay, so that's A, where we're doing work against friction. But in fact, even though we characterize friction as bad or slowing motion, it also provides motion too. Walk across the floor, there's friction between the ground and your foot. And it's in the Newton's third law pair, you push into the ground as much as the ground can push you forward. So it's friction that's allowing you to walk. And in fact, based on the coefficient of friction between your rubber shoes and the concrete floor, there's a maximum amount of acceleration that you can get. That's why you can run faster on the concrete floor than if you would take your rubber shoes and go try to accelerate on ice with them, or a different mu for wet ice. So let's take a look at that. In that case, friction is actually causing you to be able to walk. And the same thing works with a car, where you have an engine burning fuel, pumping the pistons, cranking the axle around and moving the tires, but the tires push into the ground and the ground pushes the tires forward, so it's friction that's really moving that car forward. There's also friction slowing the car down, so you have to provide enough. If you want to accelerate, you got to provide more ground push, or that ground friction, than the friction that's slowing, acting to slow motion. So if we start with the second law, sum of the forces equals mass times acceleration. And then, in this case, it's friction that's going to cause the person to, say, be able to walk on ice or pavement, depending on what it is. But friction is mu F perpendicular, the flat surface in this case. And F perpendicular is mg times ma, or equals ma. So the m's cancel, and you can see that if you want the acceleration, you just multiply it by the mu times 10 to calculate what your acceleration would be on the surface. So if we have a person, little Peter's out on the middle of the frozen lake, 50 meters from shore, okay, his mom calls him in for soup. The mu value between Peter's moon boots and the ice is 0.3. What is the minimum time for Peter to get to shore? Well, we can get the acceleration first, because that will be mu times g, or 0.03 times 10 meters per second squared, or 0.3 meters per second squared. And then we're going to set up a chart problem, simple one-dimensional one, and calculate how much time it's going to take it based on the 50 meters. So we know that this is 50 meters, the distance. The acceleration is 0.3 meters per second squared. We'll assume he's starting from rest at 0. We could do Vf squared equals Vi squared plus 2a delta S. So Vf squared equals 2 times 0.3 meters per second squared times 50 meters. Vf squared equals 2 times 0.3 times 50, or 30 meters squared per second squared. And the square root of that is 5.48 meters per second for Vf. So delta V is that divided by 2. 2.74, 5.48, and A is delta V over delta T. So delta T is delta V over A, or 5.48 meters per second divided by 0.3 meters per second squared, or 18.3 seconds. Okay, so that's just an example of how friction can cause motion. The third type of horizontal dynamic problems are train problems. And the train on the track is has very little friction between the cars and the wheels. Okay, I had a small disruption. Doing these in school, and I usually do them, in the second quarter when it's 30 to nothing or something. Bills are losing. I can come in and do them, but I came in on Sunday and my car didn't work to let me in. So, anyways, train problems. Trains have very little friction between the car tires and the track. Most of the friction comes from the engine pushing on the track and it going forward, but even that's pretty small, and it actually slowly accelerates the train up to speed. So this part here, I'm going to delete out. I meant to already. We're going to do all that now. And so in these train problems, there's very little friction between the car rims. So when we look at, say, it says what a train is accelerating at 5 meters per second squared, which is actually super rapid for a train, but just an example problem. What is the tension in each of the couples between the cars? What is the force in which the engine is pushing against the track to go forward? Okay, so the first car back here at 400, if we assume very little friction, we have that tension forward, and we have F perpendicular and FG. Okay, so in that case, the sum of the forces equals mass times acceleration, and the winner is just Ft, the green one, equals mass times acceleration. So Ft will equal 400 kilograms times 5 meters per second squared. Ft is 2,000 newtons. So you just calculate it out using your acceleration. Now, in the next car here, what's the tension in the coupling there? Well, you're going to have a larger tension because it's got more mass behind it, first off. And but not only do you have that blue tension, you also have the green tension pulling it back. And you have F perpendicular and Fg as well. And again, the sum of the forces equals mass times acceleration. But the winner here is the blue Ft minus the tension pulling back on it, which is a green Ft equals mass times acceleration. So the blue Ft minus 2,000 newtons equals a mass of 300 kilograms times an acceleration, the same acceleration, same train, of 5 meters per second squared. So calculating that out, you can see we have 1,500 plus 2,000, or 3,500 newtons. How much now is the car, the engine I mean, getting pushed forward? Well, that push force comes from friction between the tires on the track and the engine. Is that way, but we still have the Ft from before pulling backwards on it. And you have F perpendicular and Fg. The sum of the forces equal mass times acceleration, but this time we have push. The push force is the winner, and the tension behind it is the loser, equals ma. So F push minus 3,500 newtons equals 900 kilograms times 5 meters per second squared, or 4,500. So calculating that out, you would get F push equals 4,500 plus 3,500, which is 8,000 newtons. And that's the end of 5.1.